Unit 3, Periodic Table, Chapter 1. This kind of changes things on where we go with things, and now we're kind of looking at some trends in the periodic table, and actually what we'll start with is what some of those numbers mean. Last unit we mainly focused on the atom, parts of the atom, what's in the atom, where the protons are at, where the electrons are at, if you think that we can actually find the electrons, because we can't. But now we're going to look at the numbers on the periodic table and how those relate to some of the things that we talked about last unit, because there is a relationship between the last unit and this unit. And a number of times you'll find these two units put together and that they have a lot of commonalities. First couple things is that we would need to know is that the atomic number, that's usually the whole number. That's on our periodic tables. It's in the lower left-hand side of the periodic table. It's the whole number. That's also what it distinguishes the number of protons in an atom, not the number of electrons. Though in a neutral atom, both the protons and electrons are the same, they should equal each other. Say if you have 5 electrons, you would also have 5 protons in a neutral atom. But it's the number of protons that would tell us that number 5 indicates what element we're dealing with. That's the very important part of this as we look at the number of protons defines what that element is. It is very important that we understand that the atomic number is the number of protons. It also can be the number of electrons, but as we saw last unit, the number of electrons can vary. The atomic mass number is that long decimal number that we see on our periodic tables, usually in the top left-hand corner, but usually it's really nice and long and lots of decimals. And what that is actually, that number is a little bit different in that it's the atomic mass number. We're going to round a lot of these to the nearest whole number. So if you looked at, say, nitrogen and it's 14.01, we're just going to say 14. It'll make our lives a lot easier when we do some of our calculations as we move on, and so on and so forth. Now there are some that you might like, well, what do I round that to? But we'll see that. Now the atomic mass number, or sometimes we'll look at it from this equation here, is the atomic mass is actually equal to the number of protons, that's not hashtag protons, plus the number of neutrons. And so if you know the number of protons, that will tell you what one you're dealing with, and if you can then figure out how many neutrons there are by subtracting the two. Now the nuclear symbol is a way, or atomic notation, is a way of showing different ones, because the number of neutrons can actually change. It's something that we'll talk about a little bit. It's called isotopes. Isotopes are atoms of the same element that have a different number of neutrons. And atomic notation is a different way of doing that. And as you can see, we have two different ones working here, and that we have some parts here for us, and as we look at it, we can see some of the things will be a little bit different. The atomic mass over the atomic number, so it's large over the small, and you can almost use that as a way to subtract the two to give you your number of neutrons if you needed to. So, real-world example would be the ones when we have some isotopes of, say, carbon. Isotopes, again, right here, dealing with that. And we have some other parts, is that we have our isotopes, atoms of the same element, different, but that are defined by the atomic number, but have different number of neutrons. So those are isotopes. 3 common ones are carbon, those of carbon. carbon 12, carbon 13, and carbon 14. When I say carbon 12, that means I'm talking about that carbon. Carbon 13 means I'm talking about this carbon. And carbon 14 means I'm talking about that carbon. The reason why we say carbon 12, carbon 13, or carbon 14 is because if I could say carbon 6, well, they all have an atomic number of 6. So we actually distinguish them by calling them by their atomic mass number. So carbon 14 is used in carbon dating, so we can kind of see how old something is based on where how much carbon 14 is left in them. We all have a certain specific amount of carbon 14 left in us, and we can go from there. Other common ones that we see would also be hydrogen. Hydrogen has hydrogen 1. Then you have deuterium, which is essentially hydrogen 2. Tritium, which is hydrogen 3, are also some very common isotopes that we see. They don't occur very often, and you ingest them and have no problems. So not all isotopes are bad, one would look at. Since you ingest hydrogen 2, or also known as deuterium, and you naturally have carbon 14 in you. So how do we write these out, and what do we look at? Well, first off, you definitely need to have a periodic table. So I would suggest getting out your periodic table so that you can see where I'm getting these numbers, because otherwise you're going to have a very difficult time understanding where did you get that number, you might ask. Well, by looking at a periodic table, you will find life to be much easier. So the first example that we're going to do is that of calcium. Now, if we look on our periodic table, we'll see that the atomic number for calcium is 20, which we can find by, again, looking at the atomic number, which is a whole number. Now, the atomic mass, if we look on our periodic table, it's going to say 40.078. Well, I said that for this class, we're going to kind of keep that as whole numbers, and so we're going to keep that and just write 40. Now, the number of protons should always equal the atomic number, so that never changes. And we're also not dealing with a ion of any sort, meaning the same number of electrons, so it's a neutral atom, so protons should equal the electrons in this case. Now, the number of neutrons for this example are the same, and it's kind of an oddity that we have with that, and that the number of neutrons is different. I'm writing it in red so that we know that it is different. It can change for every single one. Now, the atomic symbol for calcium, 40, has us writing 40 near the top, 20 near the bottom, and then we have the symbol for calcium. Notice that I don't write a fractional line or anything such as that, as that wouldn't be needed. Now, the next one we look at is argon. Argon has the atomic number of 18. And if we look at the atomic mass, it's really close to 40, and it's 39.948. Well, I'm going to write 40 for our class. That will work, and it will work out just fine. Now, the number of protons is also going to be 18, because it should be. The number of electrons should also be 18 as well. Now, as I'm filling this chart out, I also should fair to warn you that you will see a chart like this on your probably your chapter test, as well as your summative assessment for this unit, as it will be found that way. Now, when we look at our number of neutrons, we have to actually subtract 40 minus 18 to find our actual value. which in this case is 22. And now we can see that the number of electrons and protons and neutrons are not always equal to be the same. The atomic mass goes on top. The atomic number, which defines what that element actually is, goes on the bottom and helps us identify it. And then we write the symbol for argon, which is Ar. Now, K is for potassium. If we look on our periodic tables, we can find that potassium also has an atomic mass of about 40, but the atomic number is 19. The atomic mass, as I said, is really close to 40, 39.09. So that's actually what we'll write. Let's write 40.09, or 39.09. For some reason, my eraser does not want to work very well. So I will just cross that out if I could get the right thing hooked on here. Just cross that out. And write 39. We'll circle it. Now the number of protons should also be 19. The number of electrons should also be 19. And the number of neutrons, well, that's going to be 20. The atomic mass will be 39, as it's so messy over on that side. The number of atomic number, or the number of protons, is 19, and the symbol is K. It's kind of a bad K there, but it works. Now, iron's in a little bit different situation. It's middle of the periodic table, but how we find all the numbers stays the same. So 26 is the atomic number. The atomic mass, that is 56. The number of protons still equals the atomic number. So 26. Since we're dealing with a neutral atom, the number of electrons is also supposed to be 26. And the number of neutrons, well, that's going to be, again, my atomic mass minus my number of protons, which in this case will equal 30. When writing the nuclear symbol, we have 56 on top, which is the atomic mass. The atomic number of 26 goes on the bottom. And then we have our symbol off to the side of iron. And so a chart like this would be something you'd probably expect to see a couple times throughout the chapters and units. Isotopes of an element have how many neutrons are in sulfur 33? Be careful and calculate. The atomic mass of an atom is actually very, very extremely small, somewhere on the order of times 10 to the negative 23rd or times 10 to the negative 23rd or 24th grams. To make our minds understand this number much better, we use what's called atomic mass units. Now, atomic mass units are 1/12 the mass of one carbon-12 atom. We use carbon-12 because it's one of the most commonly occurring and found atoms in nature, especially on our planet. It's not the most common, but we use it quite a bit. Now, again, the atomic mass unit, AMU, is something that we use to make these numbers make more sense instead of having extremely small numbers and having to write all these numbers and do a lot of our calculations using scientific notation, as we looked at in Unit 1.5. This allows us to not have to do that and instead give those numbers a little bit easier for us to understand. So when we look at our periodic table, again, we use that AMU or whatever it is, that mass number. It's actually known as for an average atomic mass, meaning it takes a weighted average of all the elements in the in existence for that element, such as, we look at the atomic mass of carbon. It has an atomic mass very, very close to 12, meaning that's probably the one that occurs the most. Therefore, it has more weight on that number. And, for another one would be chlorine has two isotopes, chlorine 35 and chlorine 37. Both occur in nature, but chlorine 35 occurs just a little bit more. Actually, I think about 3 times as much. I think chlorine 35 is about 74-75%, where chlorine 37 is the remainder. It's not, now the mass of chlorine 35 of chlorine is not exactly 35 because it's not in the middle. And it's the same thing with like hydrogen. Hydrogen 1 occurs the most. However, because we know there's others that do occur, that's why that number is really long and not exactly just 1. Because of that, it is a weighted average. We're going to use, again, whole numbers that will make our life a lot easier when it comes to doing our calculations. What allows us to do this is actually Avogadro's number. Avogadro's number allows us to make the change between atomic mass units, AMUs, and what's known as molar mass, and that is that you have the number of particles as 12 grams of carbon-12. It's abbreviated as the mole. We'll talk more about the mole as we can continue on. The symbol looks very similar to that of sodium, but is actually N with a subscripted A as well. And we see that I have a mistake here, and that it should be times 10 to the 23rd, and the 23 should be in superscript as well. So 1 mole is equal to 6.02 times 10 to the 23rd particles. Particles can be atoms, molecules, formula units, or whatever. You can have a mole of eggs. I wouldn't suggest it. You wouldn't be able to eat that many either. But it's just another measurement, such as a dozen. If you have a dozen golf balls, you have 12 golf balls. If you have a dozen eggs, you got a dozen eggs. If you have a dozen donuts, you have 12 donuts. If you have a mole of donuts, you'd have a lot of friends because everyone would want some of your donuts, because it's a lot of donuts. The mole is it allows us to use these very small numbers and bring them up again into numbers that are more realistic for our brain, and it actually makes our brain a lot easier to understand these numbers. We'll bring up this concept of the mole again, but it's nice to know some of the beginnings as we're getting started. So, when it comes to the mole, you can't go into the lab and say, well, I want you to give me this many particles of iron, and it just wouldn't work. Or if I had asked for measure out 6.02 times 10 to the 23rd particles of water, you wouldn't know what I'm talking about. If I said measure out 1 mole of water, some of you still wouldn't know what I'm talking about. If I asked you to go measure out 18 milliliters of water, most everybody should know what I'm talking about. And that's what allows us to kind of bridge this gap between measurements in the lab and what's going on at the atomic level, and that's again bringing up this idea of molar mass, the mole, atomic mass units, and things such as that. Now, molar mass is labeled as grams per mole. This is the label that I personally prefer students using when it comes to making our measurements in the lab or reporting numbers when dealing with the the atoms instead of AMUs, because grams per mole is something that we will be using later on in one of the units when it comes into talking about stoichiometry and doing some of those conversions. I think it's much more useful, and that's why I personally think that it makes more sense for us to use.